Welcome to Pavements, webinars for the pavement community. My name is Andrew Braham, and today we're going to talk about the development of macrocracking master curves of asphalt mixtures. And all of our work was done using a SCB sample, the semicircular bend sample. This work is based on Dr. Morales Vega's work, and she obtained her PhD here at the University of Arkansas in 2019 in civil engineering. And she's now a professor down in Panama. You can find more about her in her LinkedIn profile, the link in the comment section below. And also by Dr. Shu Yang, who obtained his PhD from the University of Arkansas in 2016 in civil engineering. He is currently a professor at Hunan University in China. So the work that they did was built off work that I did with Caleb Mudford, who was a fantastic undergraduate student way back at the beginning of my career in 2012. And what we did is we took some of the data I'd collected during my PhD thesis at the University of Illinois under Dr. Bill Butler. And what I had done there is I collected a whole bunch of DCT data, dish-shaped compact tension test data, at 3 different temperatures across various mixtures. And what we did is we collected the load displacement curves and then we calculated the fracture energy while I was at Illinois. But here at the University of Arkansas, Caleb and I worked toward taking this data, and instead of simply collecting the fracture energy, we plotted the cumulative energy curves at the 3 temperatures, and then we shifted those curves and we shifted the higher temperatures so that the end of the lower temperature would intersect with the curve of the next temperature up. And you can kind of see this wave of curves as it goes along, and then you can obtain what we called a master fracture curve. So this is just a compilation, one single curve that encompasses all 3 temperatures of testing that we did on our fracture tests in the lab. Now, if you want to learn more about this, I went over it relatively quickly, but if you want to learn more about it, you can go see the Pavements released in 2020, the development of master fracture curves for asphalt concrete. However, based on that work and based on a lot of conversations I've had with colleagues, specifically Dr. Amy Epps Martin, this made me think about time temperature superposition. And time temperature superposition can be used in asphalt materials, and we use it very frequently in dynamic modulus. So here, for example, we have 3 testing temperatures, negative 10 degrees Celsius, positive 21, and positive 54. And these were tested from 0.1 to 25 hertz. And at those colder temperatures, you can see there's higher values of dynamic modulus. That means you have stiffer mixes. And vice versa at the lower temperature. And so we run different temperatures, different frequencies. And if you talk to Jeff Rowe, he'll say you need more temperatures and frequencies. And he is putting his academic hat on when he says that, because I agree. The more data, the better. But this is just a simple example using 3 temperatures with a range of frequencies. But what you can do is you can shift this data. And you shift this data by dividing it into the 3 sets and then determining what are called temperature shift factors. And these temperature shift factors are values that allow you to move your curves to the left and the right, depending on if you want lower or higher frequency. And you get what's called a reduced frequency. And you can see that we collected data from 0.1 to 25 hertz, but now our data spans from 1 times 10 to the negative 8th to 1 times 10 to the positive 8th. So we get a much better understanding of the material over a larger range of temperatures and frequencies. I want to thank Ishan Dawe, Dr. Ishan Dawe at the University of New Hampshire for these figures. I think he made them like back in 2004 or something, and they're great. They do exactly the job, so thank you, Ishan. I appreciate it. And if you want to learn more about this shift concept, there's another Pavements, and this one was actually released earlier this year, February 2025, and it's viscoelasticity and asphalt materials. I've been thinking, though, a lot about this over time, and I've had some musings. So if you're using time temperature superposition, it requires your material to have linear viscoelastic properties. It requires so-called weak bonds, which means you need to be testing a bulk material. And when we think about dynamic modulus, you can adjust the you can adjust the loads being applied to your sample in order to make sure that your resulting strains are in the linear viscoelastic range. You can ensure that you don't have any damage because you're running the dynamic mulches. You're assuming it's a bulk material and you do not want to damage it. This is different than like the simplified viscoelastic continuum damage. You can examine literally any temperature and loading rate. You're only constrained by your equipment, so what sort of loading system you have, what sort of environmental chamber you have, but then you can use time temperature superposition to then extrapolate to lower and higher temperatures and loading rates. And this is often used in modeling, most commonly in pavement ME, ashtole pavement ME. So when you think about fracture testing is inherently a damage test. A macrocrack develops. So in the sample on the right, that loading head pushes down. You can see that mechanically inserted notch. A crack forms, a macrocrack forms, and your sample fails. So your material actually separates. And this is a case against time temperature superposition because you no longer have a bulk material. And I'm not sure of any way to ensure that you stay in the linear viscoelastic range with the fracture test. You need to talk to someone who knows more about fracture testing than me about that, but I don't think we're in the linear viscoelastic range when we're damaging the sample. So we have some assumptions, we acknowledge those, but we pushed on. We wanted to see what would happen with making master fracture curves. So again, as I mentioned, we used the semicircular bend test. This is AASHTO T394. This is the low temperature semicircular bend test. We tested kind of a range, though, of temperatures from minus 12 to 25 degrees Celsius and 0.03 to 50 millimeters per minute. And this is because we wanted to encompass all of the loading rates used on this geometry, because this is also used for the Louisiana State University, the LTRC SCB test. It's also used for the Illinois IFIT test. However, those all have, well, the LTRC test is a little different because it changes the notch length. But they all have different testing temperatures, different loading rates. So we wanted to encompass all three of these tests, all three of the loading rates and testing temperatures to see what would happen when we calculated the fracture energy, because all of those tests also, along with the SCB, calculate fracture energy. And we used four mixtures, two different nominal maximum aggregate sizes, 25 and 9.5, and two different PG binder grades, a 64 minus 22 and a 76 minus 22. And these are very common mixes used in Arkansas, and the 76 minus 22 is polymer modified. So 4 materials common in Arkansas, 4 different mixtures, 4 different combinations of aggregates and asphalt binders. And what we did is we applied a time temperature superposition principle to make a fracture energy master curve. And we got some interesting trends for 9.5 millimeters using the polymer modified material. You can see our graph here. On the left are the higher temperatures, the lower fracture energies. On the right are the higher fracture energies, the lower temperatures. So at faster loading and lower temperatures, the data was to the right and you had higher fracture energies. But this is only to a point it kind of turned asymptotical. And we did the same method here using the 25 millimeter mix and the PG64 minus 22. So the 3 other mixtures we also tested, and we just really didn't see these clear trends. Like, this kind of looks like a master curve, but it really doesn't. And so we kind of took a step back and said, well, what else could we look at? And so what we looked at was called a global fracture energy. And you can see here we have our 4 testing temperatures and our 5 loading rates. And each one of those actually created somewhat of a parabolic shape. And we could have a robust discussion, for example, like at the 12 degrees Celsius, is that parabolic? I'm not sure. Same with the 25, but there's definitely a parabolic trend with the 12, minus 12, and the 0. And what we did is we took the maximum value from these parabolas, and then we created a global parabola. And that's that line that is above all of the sets of data. And we did this with the 64 minus 22, 9.5 millimeter. We did it with the 76 minus 22, 9.5 millimeter. And what we got was this overall peak fracture energy from all 4 sets of data. And we call this the global fracture energy. And each set of 5 data had that peak and we call that the local fracture energy. So we had 4 local fracture energies, which were dependent on temperature, and then we had 1 peak fracture energy, which was dependent on, the local fracture energies were dependent on the loading rate at one temperature, and the peak fracture energy was from those local fracture energies. And what's interesting here is we get a maximum a global fracture energy somewhere between 7 to 10 degrees Celsius. And what's very interesting about this is when you look at all of our fracture tests, none of them are run in this range. They're all either run lower or higher. And it's interesting that this so-called global fracture energy peaks at a range that we don't test at. So it's not what's considered a low testing temperature, which is that negative 12 range. It's not the intermediate temperature, which is up at that 25 degree range. It's right there in the middle. So I believe this in itself is interesting. What does it tell us? I'm not 100% sure. I would love it if other people started looking at this and exploring to see, well, what can we get, if anything, out of this global fracture energy? So there's a lot more information in the paper, and if you're interested in learning more, the full paper is available online. There's the full citation. I put a link to the DOI down in the summary section below. But I appreciate you joining me today and hope you have a wonderful, wonderful day.